Alrighty. Beam of electrons, each of a de Broglie wavelength, right? So the wavelength, what is Planck's constant over the momentum, right? Incident on a thin film of silicon 30. The variation of electron intensity of the beam with scattering angle is shown, right? Okay, so here's what's going on, right? Is that we've got this thin film of silicon or something like that, right? These electrons are going in there, and they're diffracting, right? The crystals are evenly spaced, and we get a little diffraction pattern, right? So here's this central intensity, right? Is really bright, and then we've got the first dark ring, right? Maybe it's that one right there, right? And this is the first dark ring, like that, okay? So notice that is at about 18 degrees, right? So use the graph to show the nuclear radius of silicon 30 is about 4 femtometers, right? Okay. So what we're going to do here is we're going to say what sine of theta is, what is it, lambda over d or something like that. Okay. And so therefore the distance separating, and this will be the atomic diameter, right? Okay, is going to be lambda divided by the sine of theta, right? So use this lambda, plug it in there, right? The sine of the angle, make sure you're in degrees, use 18 degrees, right? And that'll give you the diameter. The diameter divided by 2 will give you the radius. I got something like 3.88 times 10 to the minus 15th, which is approximately, did I say minus 15? That's approximately 4 femtometers, right? Estimate using the result from AI, the nuclear radius of that, right? So keep in mind that, what is it, the radius to the third, R1 to the third over R2 to the third is going to be proportional to A1 over A2, right? So we've got silicon 30, the A is 30, right? Thorium-232 is going to be, A is 232, right? That's what that number is, okay? So you're going to put 3.88 femtometers in here. Where does that come from? That's just volume, right? 4/3 pi r1 to the third, right, over 4/3 pi r2 to the third, right? The pi goes away and the 4/3 goes away, and you end up with the ratio of volumes being proportional to the ratio of the cubes of the radii, right? Okay. And then put your 30 in for there, your 232 for that, your radius that you figured out here. I got 3.88 times 10 to the minus 15th meters, right? And then you'll get R2. R2 will work out, right? And I end up with 7.7. I can't remember. Maybe they used 4 or something like that. I can't remember. Okay. Suggest one reason why a beam of electrons is better for investigating the size of a nucleus than a beam of alpha particles, right? Alpha particles are complicated because if they get too close, they're going to be attracted by the strong nuclear force, right? So alpha particles are complicated that way. Alpha particles also have this problem, right? Lambda is h over p, right? Okay. So for the same energy, the momentum is going to be the same energy. I feel like the momentum is going to be worse, right? We're going to have a bigger wavelength or something like that, right? The electron wavelength is going to definitely be shorter, right? So electrons will have a better resolution. That's another reason, right? Outline why deviations from Rutherford scattering are observed when high energy alpha particles are incident on the nuclei. When the alpha particle gets close to the nucleus, right? Okay, remember there's like Coulombic repulsion. This is nuclei are positive, alpha particles are positive, right? But if they get close enough, right, on the order of 10 to the minus 15th meters, right, there's a strong nuclear force that will, grab it in, right? In fact, anything that can decay by alpha decay, you can create a semi-stable nucleus by just injecting an alpha particle into the nucleus by getting it close enough, right? It'll just latch onto it. So yeah, anyway. That's high energy alpha. The other thing is you can get, if it gets into the nucleus, if it's got enough energy, it can actually just start creating particles rather than scattering. So there's all kinds of problems with super high energy alpha particles, right? Anyway, yeah. All right, so let's see. Silicon-14 can be formed from phosphorus by a process of beta plus decay. Write down the nuclear equation that represents this reaction. Well, there you go, baby. Okay, there you've got the parent nucleus turns into daughter nucleus, right? Plus the beta plus that other particle, right? We did 1 million of these, so hopefully you'll get that right. Okay. Beta plus. Okay, sketch the Feynman diagram that represents this reaction, right? So notice that we're starting with a proton, right? Beta plus is where a proton basically turns to a neutron, right? Okay, so instead of up, down, up, it's going to be up, down, down, right? Okay, so draw your little arrows there, right? These guys don't change. These guys don't change, right? But this guy changes, right? So instead of being up, down, up, this will be up, down, down, right? Okay. And then on this side, you've got, right? You've got this guy. Okay, you've got this guy. Hopefully you're getting this right. Okay. Remember that the beta plus is an antimatter particle, right? Okay. The beta plus is an antimatter particle, and this guy, the neutrino, is a regular matter neutrino, right? Okay. So make their arrows go through time the correct way. This is time this way, right? Okay. One of them's a beta plus, one of them's a electron neutrino, right? Okay. And then the exchange particle, remember this exchange particle, on this branch you've got a positive charge because it's a beta plus, right? Okay, so this needs to be the positively charged of these guys. These are our options, right? No charge, minus charge, positive charge. Use the positively charged one of those, right? Okay, let's see. Energy is transferred to a hadron in an attempt to separate its quarks, right? Energy. So let's say we slam into it with a proton, right? Describe the implications of quark confinement for this situation, right? Remember that as you can't separate quarks, right? So as you start to add energy in attempting to separate it, instead of separating, you actually create a bunch of hadrons, right? You create these jets of hadrons, and this is, of course, what we're doing with the Large Hadron Collider. We're trying to rip those quarks apart, and we're creating all these great matter particles, right? So the energy that would ordinarily separate the quarks just turns into all kinds of nice exotic particles, right? And then it says, what's the last page here, right? The Standard Model is accepted by many scientists before the observation of the Higgs boson was made. Outline why it's important to continue research into a topic once a scientific model has been accepted by the community. Well, because sometimes models are wrong or they're not exactly right. There's further refinements you need to make to them, right? Something like the Standard Model is happening, but if it's actually the Standard Model, then if the Standard Model predicts the Higgs boson and the Higgs boson turns out not to exist, then there's some other model, right? There's got to be some other model that explains all this without the Higgs boson, right? And that's why when you find something that doesn't agree with your scientific theory, that's the most exciting thing, right? The most boring thing was to actually find the Higgs boson and go, oh, yeah, we thought it was there, and it really was there, right? The most exciting thing would be, well, it's not exactly right. And there are still things about the energy and the Higgs boson that we still need to explain. So anyway,